few, hand them back. Take a few, hand them over and around. Take a few, hand them back and around and stuff. A few here. And I'm just going to leave a couple extras here for anyone who comes in late. There should be more coming around. So just like let people grab these as they come in. There should be some coming back. Here's some here. Oh, you knew of a chunk, okay. Thanks. Okay, let's get started. All right, so just small reminders. The PA0 is due tonight. It's not due at noon. The Gradescope deadline was set wrong. It's due tonight at midnight. And we'll be releasing the first compiler assignment this evening too. There is another review quiz out due Monday morning before class. We're doing these weekly. Thanks for submitting the first review quiz. Most of you did. It was useful to see a little bit about your background because you came from different versions of 130, so that was really helpful information. Thank you. And with that, I have a handout today that I was happy about this. So the side that has some bolded text on it and sort of has 3 horizontal lines is sort of the front of this handout. It has like 3 horizontal lines on it. I managed to fit a compiler on half a page. I was pretty happy. This is a whole compiler. It's like the whole thing except for main.c. And it does something more interesting than the compiler that just did numbers that you had for you had in PA0. It actually does something useful, or very nearly useful. We'll make it be useful by the end of the day. So the first thing I want you to do is I want you to read this compiler that's on this half page, the page with the sort of 3 horizontal lines here. And the 3 horizontal lines are to fill in the answer to this question after you think about it. And this is the part of the compiler that I want to draw your attention to is this part that converts expressions to instructions. Okay? So I want you to read the front page of this, talk to the person next to you, and come up with, actually, don't talk to the person next to you yet. I want you to look at this on your own a little bit, and then we'll talk. So without talking to anybody, I want you to study this compiler on the front page of the handout and answer this question. Okay? So what assembly code is generated based on the program that's on the front of your handout? Right? What is it? Think about it for a few minutes on your own, and then we'll talk about it. Okay? For folks who are coming in late, I mean, don't be late, but I understand that there's sometimes constraints. My own shuttle was late this morning. I'm going to start leaving handouts at the back corners. So if you're coming in late, for people who happen to come in late, look at the back corners instead of coming up in the beginning for extra handouts. That's what we'll start doing after this. So this question. take another 30 seconds on your own. I know it's a fair amount of code to read, but take another 30 seconds on your own, and then we'll open it up to chat about it. Okay. Okay, 5, 4, 3, 2, 1. Okay, talk to the person next to you about this just for a minute or so. Just make sure we're all on the same page. Okay, click in again. Click in again after talking about it. Okay. All right, 5, 4, 3, 2, 1. Okay, cool. After talking about, hey, you guys, you did a pretty good job teaching each other about this. This was pretty good. So this was originally, and then more people moved towards the right answer, which was C. And so there's a couple things that could to think about for what's going on here. So at the bottom of the worksheet, I wrote out the expression form that this parses into, right? So this expression turns into, or this concrete syntax here turns into E op of, well, the outer operation is this INC, standing for increment, and it's an increment of another E op, which is a decrement, and that is applied to E num 4. That's the that's the expr that we get from parsing this thing, and so that tells us we're going to use expr to instructions on this thing, and that'll help us understand what order things come out in. And so the main thing to realize is that what happens in the eop case is we do this recursive call to get the instructions for whatever the inner expression is, and then we're putting those at the beginning of a list, right? Putting those at the beginning of a list. So the increment is going to happen last because the inner expression, this decrement expression, is what we get for the inner compilation, that inner list of instructions. And then we're putting that first, and then we're putting the add at the end. So this inc causes the add to come at the end. That tells us that C is the right answer here. So if we wanted to color code this, right, it's actually useful to think about where the different instructions here came from. The increment here is corresponding to this line. The decrement is corresponding to this line. And the number is this first line. So that's where each of the pieces came from in the output in this expression. Right? And we're working from inside out, which makes sense, right? When we do this kind of algebraic parenthesized evaluation of an expression, we expect it to go to the innermost expressions first, which are like the primitive numbers that make up the innermost addition or multiplication, and to work its way out from those. So this language that's on the worksheet, is sort of the simplest thing that can be added to just numbers, which is just allowing for increment and decrement operations. It's almost like all I added to the language was something like plus plus and minus minus. But it's enough for us to talk about what it looks like to generate a list of assembly instructions from an input expression. That's the key idea on the front side of this worksheet, is that we can talk about the concrete syntax coming in, we can talk about some interesting recursive definition of an expression, and we can talk about converting that into a list of instructions. Okay? For now, the lists of instructions we generate are going to follow a pretty simple goal. They're going to be guided by a pretty straightforward goal. It's a slogan that I'm going to repeat a few times today and on Friday as we get our first compilers written. Here's the goal. So expr2instructions takes in an expression and generates a list of instructions. And the goal of that list of instructions is to get the answer into the register EAX. The register EAX. This is, depending on what assembly languages you've seen before, like in ARM, this is R0. This is like where the return value goes. Whatever register the instruction set uses for return values. In x86, that's called EAX. It's like the main answer register. So the list of instructions we generate, its goal is always to get the answer into EAX. That means, using sort of the usual arguments we use when we write recursive functions, that this recursive call that I underlined, where we do expr2 instructions on E that corresponds to the argument to the operator, well, we know that argexprs is going to get the answer for that argument into EAX. So when we go on to do the rest of the instructions after that, well, whatever we're doing the operation on, that answer is in EAX. So if we think about this from going inside out, what happened? Well, this instruction got 4 into EAX, which is the answer for enum4. Like if our whole program was just 4, we'd want to get 4 into EAX because that's the answer. On the next line, we do the subtraction. Right, so 3 would be stored in EAX next after we do the subtraction. And that's the answer for doing the decrement on 4. And then finally, we'd end up with 4 again. This program does a bunch of work to compute 4. And that's the result of doing the answer for doing increment on this decrement expression. So each expression is, when we compile it, we're generating a list of instructions that get its answer into EAX. And we can rely on that property when we make recursive calls to say, well, we have this expression, we need to know its answer. I'll compile it, that list of instructions will get the answer in EAX. Then the rest of this compilation step can rely on that. So this is the slogan. We'll keep seeing this over and over again, this idea of getting the answer for an expression into this EAX register. And that's going to be one of the main ways we organize the compilers at first. Later on, we'll see how to use more space in different registers in useful ways. But this is a nice organizing principle to get started. Any questions about the code on the front of the sheet before I go on? Talk about it, actually. Generate questions. Look at it, talk to the person next to you. Generate questions about the code on the front of this sheet. If you have any questions about this code before we go on. So the code they're going to write more is on the back side where there's all these fills. So we'll be doing that in like 10 minutes. Okay, cool. Any questions? Any questions about the code on the front? Questions about this? Questions? Everybody's, yeah, go ahead. If you wanted to make it more robust, give me an example of what you mean by more robust. So if we wanted to match with more than increment and decrement, like as we start adding things to our language, right, we will start matching on more kinds of S expressions that match those new expressions we're adding. And that's what we're going to do. That's what we're going to do on the back, is start adding new expressions and see how that propagates through this whole compiler. Right, now we have this nice structure where we have parse, to an expr, and then take an expr and generate a list of instructions, and we can start iteratively adding to both of those functions and changing them if we need to change their signatures or anything like that. Other questions? Okay, cool. I want to make just one notational note. This is going to go pretty quick. Here, I'll hide the questions for a second. One thing that I think everybody has seen in some form, but I just want to make sure I write it on the board in class once, is the thing that's up here in the top left, right below where like the module exports or the module imports happen, looks like this. It says expr is either a number or it is some operation applied to some expr. And then it says an op is either inc or dec. Right. That's the description. It's in the top left. This is called a grammar. It's the word I'm going to use to refer to these things. And this kind of context-free grammar is, usually talk about it in a theory class, and depending on which version of 130 you have, you might have even talked about writing interesting parsers for these things in different ways. But the idea is that this describes which S expressions we want to allow in our concrete syntax. This describes which S expressions we want to allow in the concrete syntax. In particular, here, one of the expressions in our language could be a number, could be some just primitive number, or it could be in parentheses two things, the first of which is an operation, and the second thing which is any expression, which could itself be a number or some other operation. Right? So this is a sort of a recursively defined way of writing down the shape of concrete syntax. And this is in contrast to the abstract type, right? This is how we define AST. We write type expr, and this is the thing that had enum of int and eop of, and I just wrote these as, I wrote an op type here, op. Okay. And so this is the definition of the abstract syntax tree. Right? This is the type of the abstract syntax tree. And what our parser does is it takes strings that match this grammar, checks that they match the grammar, that's why we match on specific lengths, and produces elements of the type of the abstract syntax tree. Okay? And so I just want to make sure everyone knows we can sort of read this grammar. So the second question, we're going to add something. But let's answer the first question for now. So answer this question right now. Let's just make sure we understand how to read these things, okay? Which of these matches the grammar on the left? I'm going to only open this up for about 15 seconds. There's a trick question in here. I'm going to warn people when I ask trick questions. There's a trick question in here. Okay. 5, 4, 3, 2, 1. Okay. Yeah, so the only one of these that matches this grammar is C. This is the only one that matches this grammar. It matches this grammar because it has in parentheses an operator, and then the second thing is also an expression, which is an operator followed by a number. A doesn't match because there's no plus in the grammar that I defined. We may well someday want to make plus work. In fact, we'll be making that work very soon. And then B, there's no way to have two expressions after an operator. D, there's no way to use inc and dec in other places. And E, we don't have anything in the grammar that talks about using names like that yet. We soon will, right? It definitely we'll definitely want to talk about programs that use variable names, but that's not in the grammar on the left. Right? That's not there. So C is the only thing that matches this grammar that shows up on the left. Okay, cool. So the next thing I want to talk about is adding variables to this language. So this language just has increment and decrement right now. It's useful for seeing the different pieces of the compiler. Let's start adding some things that make this feel like more of a real language. Okay. So I'm going to add a particular way of defining variables. It's going to feel a little bit like we define variables in OCaml, and it's going to be useful for talking about what it looks like to have a scope for a variable and what the meaning and semantics of variables are. So I'm going to use the keyword let, and then in another set of parentheses, we will have a name for the variable that we're defining. Then we'll have an expression, and then we'll have another expression. And the idea here is this means that we'll define some name to be equal to some value. That's the first expression in the inner parentheses. And then anywhere in the expression, the second expression, we can use that name, and it should have that value. This is defining a new name to be mapped to some value, and that value comes from the first expression. Okay, and we're also going to need one other addition to our grammar, which is to talk about the identifiers themselves, right? Using a variable, right? That's now a kind of expression in our language, right? Our language previously had numbers and these operators we could apply to them. Now we want to allow ourselves to just write down the name of a variable and have that mean, well, evaluate to whatever value this variable has right now. So we need to be able to express that. Okay. So just a quick check-in. Given that I added these things to the grammar, and assuming name means right, some sequence of characters for some name of a variable, which of these matches the grammar over here that's extended with let? These matches that. Okay, 5, 4, 3, 2, 1. Okay, great. Yeah, so this is B. Okay. We need that extra set of parentheses, and this has the keyword and this correct nesting. Okay, so the back of the worksheet, the other side of the worksheet, is basically the compiler with blanks for us to fill in the implementation of making this work. Okay? We're going to fill in how we bind a name to a value, how it gets stored, how it gets looked up. Okay? And that's going to be sort of our first way we start to use, we start to really like dive into defining interesting features. Okay, so let's start by, we just added to the concrete syntax, to the grammar for the concrete syntax, so we sort of know what it's supposed to look like. Which of these is a reasonable definition for us to add to the abstract syntax definition? Which of these is a reasonable variant to add here? So let's just talk about the let case. What should we be adding to the expert type for this? Think about this on your own first, and then if there's enough disagreement, we'll talk about it. Okay, 5, 4, 3, 2, 1. Great. Talk about this a little bit. Let's talk about this a little bit. I'm just going to scroll up for a second so I can get that grammar back on this page too.
When we were doing that, basically what you wrote over there, where you have let, name, and then expression, and then another expression, the example you showed, you have like let x5, and then the whole thing was 9. Now, does that mean the x is equal 5, and then the whole expression is equal 9, or, okay.
Exactly. It's like we didn't use x.
Okay, so now x is basically going to be equal 5, and then the whole expression is going to be equal 9.
Yeah. Yeah.
What is that going to get used for? I mean, like, I'm not saying we're...
Let's talk about a few examples in a minute. Yeah.
Okay.
Yep.
Okay.
Yep. Okay, cool. Just clicking again quick. Okay. Okay. 5, 4, 3, 2, 1. Okay, great. So if we want to represent this case in the grammar, there's 3 pieces we need. We need to represent the name that we're adding a binding for, the expression that represents the value it'll get, and then the expression that represents the body of this let expression, what it'll evaluate after we do that. So in this case, it's C is the thing that lets us represent those things. In case A, there are 3 things, but the first thing is not an expression. The first thing is always going to be the name of some variable. It's not like we could put 5 here, right? It wouldn't make any sense to have a variable declaration where we put in the name position like 5 or 5 plus 1 or something like that. This is always going to be a name. So it makes sense to say the first thing in our abstract syntax is going to be a string that represents that name. Then the other 2 things could be any kind of expression. Okay, so that tells us what elet should look like. Someone asked a question that was pretty good while I was walking around. So I want to bring back the example that was on the last page where I wrote this, and they said, look, that's nice, Joe, but this program seems a little foolish. What should this program evaluate to? 9, yeah, it bound x to 5 and then it ignored it. Right? Okay, let's make this program a little more interesting. Right? So this should, we should expect 9 as the output here, right? And let's like increment x in the body here. What should this program evaluate to? 6, right? Okay, so just to be clear, that let x5, 9 program is sort of silly. It's a binding this variable that it doesn't use. But this is the kind of thing where we can now start to talk about creating a variable and then using it later, right? And we expect that to evaluate to 6. As programmers, we have a very strong intuition that that had better evaluate to 6, right? And that's you know, what we're going to use as let bindings in this course. Okay, do we need any other cases in expr in our abstract data type? Right, if we add this elet, are we done? Yeah. We need to define what happens when we get to these name expressions, right? We're going to get down to these name expressions, like in this example that I just wrote. When we get down to this use of the variable, that's going to correspond to using a name and having an expression that matches a name, right? That's exactly going to correspond to that case. Okay? So we do need one more case in expr. We need to be able to represent, I'm going to call it EID for identifier. Okay? So we're also going to need something that can represent using a variable. This is an expression that represents looking up the current value of a variable or using a variable. Okay? All right. So that tells us, that gives us our new data type. We've extended the data type. And this is how I'm going to think about adding features in this course, right? This is a pretty simple feature, but as we go forward through the next 2 or 3 weeks, we're going to keep adding features at a pretty rapid clip, right? We're going to quickly get to more and more interesting features to add to this language, and the way we're going to process it always to say, what do we want it to look like to the programmer in terms of the concrete syntax? What do we need to add to the abstract syntax in order to make that work? Then how do we parse it and how do we compile it? Okay? So let's run through that process now, right? So the next thing we need to do, we know what abstract syntax we're aiming for. We know what the concrete syntax for this looks like. We should be able to write the parser for this now to get from concrete syntax with S expressions into this abstract syntax. That's the next step. Then we can compile it to instructions and watch it run. Okay? So let's talk about that next step. So on the left-hand side, I have set this up with, actually I'm going to hide the question for now because I want you to think about this on your own for a minute, and then I'll bring the question back. So this is on the back of your worksheet. This is taking in an S expression and producing an expression, something from our abstract data type, our abstract syntax tree, sorry. And there's 2 blanks in it, right? So one blank is when we have a list of sub-S expressions where we're matching inc and dec before for increment and decrement. And that's where we should be adding the case for elet, right? Because elet is going to be some parenthesized expression. I also blanked out the atom case where we were previously using string event to expect there to be a number there and just parse a number, because now it could be that that string is a number-like string, or it could be that that string is a variable name. Right? Those are the new things that could happen in this function. Okay? So I want you to try filling in these. Focus on the elet case first. We'll come back to the base case, the atom case, but focus on the elet case. So focus on filling in this elet case with something that will take in atoms of the elet shape that we talked about in the grammar and produce instances of that elet variant we talked about on the last slide. Okay, so try to do this for a few minutes. Feel free to talk about it. Just dive in and try and do this for a few minutes. Okay, try and fill in this case. So that's going to come when we compile it later, right? Because this is when we're creating instructions from the expression, right? And so this is where we're trying to take in and this expression is going to. Thanks, Microsoft Auto. So we're going to take in some S expression. It's going to try and match this grammar we talked about. You produce an elet, right? We should be producing something of type elet, the thing, that you wrote in here. So we should be producing one of these when we find the syntax that matches let name expert. Is that a helpful explanation?
I'm just sort of like confused what you would like with this password.
So these are producing EOPs with particular operators because we matched an inc followed by some arc in parentheses. Here you have, it's going to start with let, but we want to match this shape. What's this shape going to look like as a bunch of atoms and lists, right? And then we want to use those pieces to produce the elet. Okay, I'm going to put some options up for you to look at. I like having you work through these as much as possible, but I also like getting to the end of things. So it's useful. Most of the use is in having I don't expect you to be able to write these things when I do this in class. It's worth saying this. I don't expect you to be able to write these things correctly the first time I put them up. I mean, like learning science tells us if you struggle with something before you're shown options or shown the answer, it's way better for you. So that's why I have you try and do these things on your own before I show you options sometimes, so that you are now thinking about whatever you were trying, and now here's some potential options. Okay, so I'm gonna open this up for you to click in and pick the option that's going to work here. Okay. 5, 4, 3, 2, 1. Talk about this for a minute. Talk about this for a minute. E. Because there's 3 pieces to the let. If we think about, like if you look at this example.
Yeah, E, but E only has a.
Oops. Sorry. I messed this up just a tiny bit. Let me get the right thing here. What's wrong with E? What's wrong with E?
Oh, so it's never E, right?
Yeah. Because the let is always going to make 3 pieces, right? It has the let atom, then it has the binding part, which is one parenthesized thing, and then it has the body. And so there's 3 pieces inside that parentheses. Then we have to intermatch on that nested thing. Okay, cool. Click in again. Click in again. Okay, let's see. 5, 4, 3, 2, 1. Okay, so I wrote down here an example of what this is going to look like to get from concrete syntax. Right? Maybe I'll even put a string around here, string quotes around here to be clear. Right? This would come as input to our program as just a string containing these characters. Right? A string containing open parentheses, let space, and so on. Then we'll use the S expression, the built-in library for parsing S expressions, this thing that's in like all programming languages have this as a library. And then we get back this list structure. So the list structure is going to have, oops, I wrote num in a few places where I meant to write atom. Everyone should be aghast at my sloppiness. Okay. So we're going to get this nested list structure, where we have the keyword let at the beginning. That's just an atom. That's the string let. Then, since we see another set of parentheses, in parentheses then, we have that creates another list where we have the atom x followed by the atom 5. That corresponds to the x5 part of this. That's one of the key things to notice one of the sort of the key insights to get this laid out correctly is that this part of the input concrete syntax is going to correspond to a nested list in the S expression type. Right? So that parentheses x5 turns into another list right here. And then the other 2 pieces that are inside this outer set of parentheses are the atom for the sort of the keyword or just the string let, and then the atom for 9 at the end. And our goal is to get to an E-let expression in our abstract syntax tree that has the name x, the value, the expression for the binding enum5, and the expression for the body enum9. So that's the goal for the workflow here. Now, there's 3 things in this list, right? That's actually one of the critical things to observe, which immediately rules out which letters. There's 3 things in the outer list. What does that rule out in terms of letters? C and D, because C and D match on 4 things, right? So this is 4 things, and this is 4 things. And neither of those match what structure we'll get from the S expression here. Right? None of those match that concrete syntax. So there's 3 things in the parentheses. So it's not going to be C, and it's not going to be D. Okay? The others do match on 3 things. They have the let keyword followed by the bind followed by the body. What's wrong with A? What's wrong with A? What's the issue with A? It's not recursively calling SX to expr. It's not recursively calling it. Why is that a problem? It seems fine. I'm making an E-let with the right pieces. Yeah. So if we look at E and body, right, these 2 pieces, so both of you are right. It's just useful to have it described both ways. Right? If we look at E and body, E-let is expecting those things to be abstract syntax tree typed things, right? They should be exprs, right? But E and body are just either atoms or lists because they're parts of an S expression. They're just atoms or lists. And so we'll get a type error here that says, well, you're trying to construct an E-let, but these things are just S expressions. You haven't parsed them. You haven't turned them into abstract syntax trees yet. And E-let needs abstract syntax trees in those positions. So that's why A won't work. Okay. How about B? So B does the recursive calls on E and on body, so it's going to be the right types there. Anything wrong with B? Anything wrong with B? Yeah. So name here is some S expression. We actually don't even know if it's an atom or a list, but name is some S expression, because that's what's in one of these list of S expressions. And E-let expects a string in that first position. So here, the problem is that the type error we'll get is that E-let expects a string as its first argument, and we gave it an S expression. So that's why B won't work. Okay. So E is the one that works here. It says we need to have an atom that's let followed by a bind body. We match the bind and make sure that there's exactly 2 things, and we get the string for the name out, and then we use that as the first argument to E-let and recursively parse the other 2 pieces. Okay? So E is the only one that works here. The other ones will give some kind of error. Either C and D will match on the wrong number, and the others will have a type error. They won't go through the OCaml compiler. So E is the one that works here for getting the syntax of this thing. Okay. Let me just go. I'm just flicking down. Okay. So that's what it looks like to get the case for E-let. The case for atom. Any suggestions for what we should do in the case for atom, where we're trying to decide between a number and an identifier? What should we do for atom? What should that case look like? In English, if not in OCaml code. What should that case look like? What do we need to do there? Some kind of check we need to do. What kind of check do we need to do? Check if it's, yeah. So when we get down to this atom case, if S contains all digits, it's a number. If S contains a name, then it should be an ID, right? And we need to decide between those things. So we could write this check in a lot of ways. I'm sure in your programming life you've written things that map over a string and check if all of the characters have a certain property. One way to do this would be to, there's a function that I mentioned at the end of class. I just want to bring it up again. Int of string opt, which takes in a string, and it'll return none if it doesn't match being all digits. Right? So if it's not all digits, it'll return none. Otherwise, it will return some of an integer. And if it returns sum of an integer, we would want to construct an enum of that integer. If it returned none, well, then it's probably a name, but it also could have all kinds of like backslashes and semicolons and other things that we might not want to be part of names. So we might do more checking here, or if we wanted to be expedient because we're in class, we might just say, well, we're gonna trust for now that everything that's not made out of digits like a number is just gonna be some name like X or Y, and that will construct an ID in this case when it's not, when we can't parse the string as an integer. Okay. We could definitely add more checks there to make sure it's like all ASCII characters A to Z or something like that. There's more things we could check. Okay. So that's parsing let expressions. E can just slot in there. And then if we have these IDs that we want to insert also, we can add them in this atom case. And that'll get us to let expressions. That'll get us to having the abstract syntax, at least, of defining and using variables. Of course, we haven't implemented the compiler for these, right? Now we need to talk about what instructions they're going to generate. We need to talk about what instructions they're going to generate. So also on the backside of the handout, I have a gap for where you're going to put, what you're going to put in the let and ID case of expr2 instructions, expr2 instructions. I actually want you to think about that for a minute, maybe just talk about it for a minute. In expr2 instructions for the let and ID case, what do you need to add in that case? What do you need to add for expr2 instructions for let and ID? Talk about that for a minute. Just talk about it. I don't know, I'm not going to show you options. We don't have enough time to go through it all, but talk about what you need to make that work. Okay. So I'm talking about this case here. Oops. Talking about this case here. Okay, let's just talk about this for the last minute. What ideas did people have? What ideas did people have from talking about this? What ideas? Or problems, or things you can't do? Yeah?
I think that like you need to keep track of the variable value when it comes to names. So we should maybe carry on a map that tells us which name belongs to each like register.
So one idea is we're going to need to somehow, when we get, let me say it from this point of view, when we get to compiling an ID expression, we need to know, like, where is the value for that variable, right? We're going to have some string that represents the name of a variable. We have to go find the value for it somehow. So maybe one thing we're going to add to this is some map that keeps track of a mapping between names and values, or names and locations, something like that. Other things, other ideas that people had when thinking about this. Other ideas. Yeah? So the first answer mentioned registers, and you're mentioning memory, right? Which there are two places in the machine where we could store data, right? And we'll need to think about this notion of where the value of the variable is. Will it go to a register? Will it go to memory? How many variables could be fitting in registers? Eventually, it seems like we'll have to use memory because we have a finite number of registers, and there's nothing saying you can only have 8 or 16 variables in your program. So it seems like we're going to need to talk about memory.